Where is it? Sekarang dah sharing ke? Present now. Window. A video. Movies or TV. Saya nak play. Oh, benda ni kacau. Okay. Alright. Okay, image parameter method have three techniques, three methods. So we have today we'll discuss about the K section method. So image parameter method basically depends on two ports network. We have input and output. So we do the analysis from both left and right, input and output. So however, this technique has disadvantages, especially on the frequency change, which affect on the impedance, both input and output. So, however, people are using this method because it's very simple. Not the other one, which is more better, but it's a bit complex. So another one is called the it's just a loss method. Okay, using the constant K filter, basically we have the T form and pi form. So this is a low pass filter. So this is the T form, while the pi form on the right. Okay, so basically the formula is there. R0 is equivalent to square root of L over C, and omega C is equivalent to 2 divided by LC. Okay, so if R0 and omega C is given, so you can find the L and C. So either you want to use T form or pi form is okay. Okay, that one is for low pass filter. So this one is for high pass filter. So you have the this one for high pass filter, T section, and this one for high pass filter. Okay, in constant K filter section, so you will have a pass band and stop band. Where pass band you allow signal, while you at the stop band you eliminate the signal you don't want, and is within the cutoff frequency. If omega is below omega C, so it will allow pass band. If omega more than omega C, so it will stop the signal. So in K filter section, image impedance is a function of frequency. So what it means by this, the impedance are changing. So instead of, for example, you want it maintain at 15 ohm, but it changed when the frequency changed. So this is the normal graph of the constant K filter. So the value of ZIT and ZI pi, so this for image for input and output, is equivalent to R0 only at omega equivalent to 0. And it has a very low attenuation, so near the cutoff frequency. Okay, so this some exercise you can do in the class. Stop dia tak boleh aku ni. Okay, so tak nak ni, saya tak nak lah. Saya stop ni. Stop sharing. Back to the entire screen. Baik, saya cakap je lah. Okay. Mana tadi? Saya sendirilah cakap, tak payah tengok video. Okay, so this some exercise during class. So I taken this in order maybe some basic question. So the first question example here, in low pass constant K filter section, the value of L and C are given 0.3975 nanohenry and 0.159 nanofarad respectively. So find RO for low pass filter K section. So how to solve this? So we need to look back on the whether this is for T. If for T, we can for T section. So we can use the basic formula R0 equivalent to LC, and from that you can calculate. So where R0 equivalent to L over C is coming from? So we look at this formula. So this is the formula for R0 equivalent to square root of LC, L over C for low pass filter. So this is just a direct question. So apa jawapan dia? So jawapan dia saya pun tak tahu. For 50 ohm. Okay.
Sir.
Yeah.
Value of L tu nano negative 9 kan?
Yeah. Yes.
Dalam
saya rasa different value ni. I think this is micro ni. Okay, wrong question. I think it's micro Henry and nanofarad. Okay, thank you. So from this calculation, you can have R0 equivalent to 50 ohm. Saya tak perasan ni. So normally question design lah. Okay, second question. The values of L and C are given. Okay, for the low pass constant K filter section in T form, find the value of cutoff frequency. So this one also a direct question. So you can calculate based on using, because L and C is given. Okay, so you can calculate omega C is equivalent to 2 over square root of LC. Okay, so this just for basic starting of designing the filter. So this just a direct question. So I have done the video, but never mind. I will later upload new YouTube. I think playing from YouTube directly is better compared to when I play directly from my computer, from my hard drive. Okay, so this you can calculate by yourself. I also forgot which is the answer. Okay, I think the answer may be A. All right. So basically, the K filter, okay, for low pass filter, you just need to know the value of L and C, okay, or you know the R naught and omega C in order to calculate the value of inductor and capacitor. But you need to know the form, the structure of this low pass filter. Okay, constant K filter section, yeah, this has a problem. The problem is, first one, the signal attenuation rate after the cutoff point is not very sharp. So it is not considered we want to cut off at 2 gigahertz, but it will go maybe 2.5 to 3. So it is not maintained at 2 gigahertz. So the attenuation rate is not sharp. Second problem is the impedance. It is actually because of the impedance is changing based on the frequency change. So it will create mismatch due to this problem. So as solution, mana ni ya? As solution, so the second technique is introduced. So the second technique here is called the m-Derived filter section. So m-Derived filter section is a modification of constant K filter designed to overcome the problem of slow rate of attenuation and variation of image impedance. So the slow rate refer to the non-sharp cutoff frequency. The second part is basically on the attenuation where the impedance are changing based on the frequency. Saya boleh conteng. Okey. Kan? Boleh. Okay. Okay. If you can see this one, so this is the constant K. So it's supposed to go sharp like this m-Derived, but it keep on changing the impedance based on the frequency. So the red one here is the constant K. It changed because of the impedance changing because of the frequency change. So it doesn't get the sharp cutoff frequency, and the attenuation also keep on changing. So number 2 here, m-Derived is introduced in order to get the okay. So number 2, m-Derived is introduced. We can get a sharp cutoff frequency at this omega infinity. So basically, we can call also omega C at the cutoff frequency. Unfortunately, also for m-Derived, it is not maintained. It's supposed to be maintained approximately at a certain attenuation here. So it's D line, for example. Unfortunately, for m-Derived, if it goes down after the omega infinity, okay, if we go down, then we introduce, in order to maintain the attenuation, so we introduce the number 3 method, which is composite method. So this composite will maintain, so approximately here, okay. So it maintain at the certain attenuation. So now we proceed with the second technique, which is T-form m-Derived filter section. So the same as K constant, okay, basically you can have the T and pi form for both low pass filter and high pass filter. But in my slide here, okay, so I adjust show for using T form for low pass filter and high pass filter. So I only showing the T form. Okay, in m-Derived filter section, so you have this m value. So this m value at each of the inductor and capacitor. So what is this value? So this value actually you can choose whether you want to have, if it matching. So if m equivalent to 0.6 is for matching. So it will maintain uh, at the certain attenuation. For example, when frequency change, so the attenuation will maintain at almost the same level. So you can choose m, which is less than 0.6 or more than 0.6. So you can calculate m basically based on this equation. M equivalent to square root of 1 minus omega c divided by omega infinity to the power of 2. So normally m is chosen which is less than 0.6, maybe the best 0.3 and so on. Okay. So here the formula for low pass filter, okay, still it is using from the K constant value. So the same formula is using here to calculate the R naught, omega C, L, and C. So as the same as if R naught over omega, R naught and omega C is given, you can calculate L and C. And if L and C is given, you can calculate R naught and omega C. But here, okay, at both arms of the inductor, you still need to multiply it with the m value. Next. Okay, here the simple image impedance of the m-Derived low pass filter network. So here is the attenuation level. Okay, so if it's perfectly perfect attenuation is at R naught, for example, for this impedance value. So when you choose m equivalent to 0.6, so it maintain almost near to the R naught. So this is actually for matching purpose. But if you reduce it to less than equal to 0.6, so it will change based on the frequency which is lower value than R naught. So if m is bigger than 0.6, so the value will increase, which is more than R naught. So basically this is for the as a reference for the image impedance. So choose M wisely in your design. Okay, this is a simple example for low pass m-Derived section. Okay, it introduced an infinite attenuation pole at 2.05 megahertz, while the cutoff frequency is at 2 megahertz. Find the value of m. So basically, so this is the F infinity. So this is FC. Okay, so the formula to calculate m is equivalent to square root of 1 minus omega c divided by omega infinity to the power of 2. Since omega is 2 pi over 2 pi, so you can replace it just fc over f infinity. So here m equivalent to this, you just include the value of the frequency and you can choose which one the answer. I also forgot. I think maybe this is the answer. Oh, this. Sorry, I forgot. I have calculated it, but now apa jawapannya? Saya pun tak ingat. Okay, this is the answer. Oh, here B is equivalent to 2.1, 0.21. I think 0.21 maybe C. Okay, never mind. You can calculate it by yourself after this. Okay, second question. Low pass m-Derived section with m equivalent to 0.197, L equivalent 3.18, and C equivalent to 1.27 nanofarad. Find the value of inductor in shunt arm. Okay, so the question here asks to find the value of inductor in shunt arm. Okay, shunt. So actually it wants you to calculate this inductor. So you just use this formula 1 minus m to the power of 2 times L divided by 4m. So m is given here, m is 0.197. So you just include the value and you can calculate and you get the answer. Okay. So basically this image parameter method is for low frequency. All right. I don't know which the answer. Maybe A. Maybe.
A, sir.
Yeah, A. Or you have calculated.
Yeah.
Okay. So actually I'm planning for you to calculate. Okay, good. Okay, the answer is A. Okay, next. The high pass m-Derived pi section with m equivalent to 0.28 and C equivalent to 21.22 nanofarad. Find the value of capacitor in the circuit. Okay, this one is not in the slide because in the slide just now only show to you the T section. So here is the pi section for high pass filter, which is the parallel part is the inductor and the capacitor. So here it asks to calculate the value of capacitor in the circuit. The only capacitor in the circuit is here. So it's just a simple C divided by M. But in order to understand the question, to answer the question, so actually you need to you need to know the circuit form. So this one is the pi section. So you sketch it and you know where is the location of the only capacitor in high pass m-Derived pi section. So ini jawapan yang mana? Anyone? D. Okay. Alright. Actually, I have the answer here. Okay. Correct. The answer is D. So this is the second method of image parameter method, which is we are using the m-Derived filter. And finally, okay, the composite filter. So we have this composite filter. So composite filter is to improve K section and m-Derived. So by combining both technique. So by doing so, filter with the desired attenuation. So we got the desired attenuation and the matching properties can be obtained. So you want to have the desired attenuation and the matching properties can be done. How is it? Okay. So actually, when you are using the composite technique, the third one, so it's combined. They are using m-Derived. You have the sharp cutoff here, follow the red line, and then it maintains the attenuation, okay, using this red line. That's how it is done using the this technique. Mana ni? Pointer. Color. Okay. Okay, so next. So composite filters, basically you have we have a final 4 stage of composite filter, which is combination of constant K technique method and m-Derived filter technique. So it combines this with a matching section for both input and output here. So we have the both combination of K, constant K, and m-Derived section. And we have matching section for both left and right. So you have from the book. So I take this from the book. Okay, the same value of LC for constant K, the same value of m-Derived value, and the form for pi section for the input and output. So let's see example here. Design a low-pass composite filter with a cutoff frequency of 2 MHz and impedance of 75 ohm. Place the infinite attenuation pole at 2.05 MHz and plot the frequency response from 0 to 4 MHz. Okay, it is given the impedance 75 ohm. R0 is 75 ohm, FC 2 MHz, F infinity is 2.05 MHz. So in order to design this, okay, you need to know the form of the final 4 stage. Okay, let's see, we solve the constant K first. Okay, using this formula. So we can get the L equivalent to 2R0 divided by omega C. So R0 is 75 ohm, omega C is 2 pi FC. So then you can get the L and C value. And you include this value in this circuit. And you got the first section, which is the K section. For the M section, okay, kita tukar color lagi. Okay, we use this formula. Again, we know the FC is 2 MHz, F infinity is 2.05 MHz. You obtain the M equivalent to 0.2195, and you include everything in this value. Okay, so you just include it's missing something. Oh, okay. You already know the value of L here and C. So you just include here, and you got the ML over 2, ML over 2, MC, and 1 minus M to the power of 2 divided by 4 ML. Okay, so this is the value of M. You can see that this value Fm is less than 0.6. in order to get the, I think, among the best form of low pass filter. So now we have solved for two stage, which is for the constant K and m-Derived. Now we want to solve for the matching section for the input and output. So we go to the next page. So this is the form for matching section. Okay, only now the value of m chosen for this for matching is m equivalent to 0.6. So L, you know the value of L already, and C, you also know the value is already. So you just calculate this, and calculate this, and you put the value in the input section and output section. And now you already know all the four stages. So you just include, okay, so this the matching part for the input and output is similar. And for the K section, so this is the K section, and this is the m-Derived section. So if you have the computer aided software, okay, actually when you run the simulation, you can for the S21 to get the frequency response, so you can get the sharp cutoff at 2 megahertz. So at the cutoff frequency, and it goes here also. You can see the first pole, which is due to 0.2195, and the second pole is for the m equivalent to 0.6. So these the poles. Okay, so it's almost the end of my class. So basically, so today class is focusing on the image parameter method, which is stop presenting. Okay, which we have three methods with three techniques, starting from K section, then we move to m-Derived section, and finally the composite filter design. So actually, so for this, the first time in 5 years I teaching this subject, I include this section, which is using the image parameter methods. Normally for filter design, I will go directly to the insertion loss method, which is more focusing on this microwave design. Anyway, this is a knowledge, or maybe I can also ask in the test or whatsoever related to this technique. So this technique also you can read from the microwave engineering book in order to know more details, especially on the derivation from the two-port networks, if you want to know more. So because for me, to facilitate this course, I just go through, especially on the forms, I mean the structure, and directly the formulation in order to calculate the low pass filter or high pass filter. So next week we will go to the filter design by using the insertion loss method, and following to that also. So maybe I will give a CAD computer aided design assignment in order for you to design the filter. So anyway, on our next class on Sunday, so we will proceed with the insertion loss method for this filter design. So it's 12:50. Any question? Any question to today's course?
No, doctor.
No, doctor.
All right.
Oh, sorry.
Okay, actually I have recorded all these 3 videos. You can go through. I will upload in the website just after this. All right. Okay. If no nothing, we end our class now and see you on Sunday. Saya dah ambil kedatangan ke? Tak dia. Tak, tak nampak pun. Oh, normally it will automatically. All right. So thank you.
Thank you, Doktor.
Okay.
Okay.
Tinggal apa? Submit aja lah tinggal. Okay, you can left the meeting. Nak stop recording. Lupa.